Welcome to Math 119, Chapter 6.1, where we talk about exponential functions. So let's take a look at what we have covered so far. We've had linear functions of the form f of x is equal to mx plus b. We've had quadratic functions where we have ax squared plus bx plus c. And then polynomials, very similarly related to this quadratic, except it's not any degree of 2, but it could be 3, 4, 5, or more. And the setup is very similar. So you have your leading coefficient, lots of terms in the middle, and then your constant. Then we also graphed rational functions where we just have a polynomial above and below. So today what we're going to be doing is your exponential functions. Now, exponential functions have the form f of x is equal to a times b to the x. Now you can have lots of variations on these types of exponential forms. You could always add something to the outside. You could always add and subtract things to your exponent here, as well as you might not even have what a is called, which is a multiplier. So a is called a multiplier, which we'll discover what the multiplier does later on in this video. And b is called your base. And now what's new is that this x, your variable, is now your exponent. Unlike before, where you had your variable down below, and then your exponent would be a number. It's going to be the reverse. This base is going to be a value, a number, and your variable x is going to be right there up in the exponent. Now let's take a look at what your restrictions might be for an exponential. So with your base here, base b has to be greater than 0, as well as your base is not able to be 1. Now let's take a look at why that might be. So your base b being greater than 0, right? We're dealing with non-negative numbers. The reason for that is if b is less than 0, so a negative number. Let's say b is negative 5. And let's take your variable x. Let's say x is 1/2. So we now have, and we'll just say a is 1. So we now have f of x, or f of x is now, well, actually, we'll take it this way, b to dx, right? If a is just going to be 1, it's just itself. So it's, we're going to evaluate at -5. No, not -5. Let me reverse that. So we have b has -5x. So if x is 1/2, you now have -5 to the 1/2. So that's a square root with a -5. Is that possible? No, so we're not going to be able to have a negative base here because your exponent, right? Your exponent matters what the value or the degree is, because we cannot evaluate certain values. So that's why we have this, your base being a non-negative number. Now let's take a look at another restriction where b, let's say if it's not equal to 1, let's say it is equal to 1. So let's just take f of x is equal to 1 to the x, and then let's just set x equal to 4. So if we have f of 4 is equal to 1 to the 4, well, that's just 1. Okay, well, not bad, but let's change it. Let's say now x is 5. So f of 5 is equal to 1 to the 5th, and that is also equal to 1. Right, so what's going to happen if you have a base of 1? Well, if you have a base of 1, and even if you're changing your x value, you're going to come up with a solid straight line. So if base is 1 and x changes, we will get a line. So that is why b has to not be equal to 1. You can still plug in a 1 into your x value and a 0 into your x value. You just cannot be equal to 1 or greater than or any sort of negative for your base because of these restrictions. So based on what your x value is up here might restrict what your b has to be. Or when b is 1, right, no matter what your degree is, you're always going to get out a 1. So that's why this one is going to be the restrictions of those. Now let's take a look at your exponential functions in a graphical form. So let's just take a very regular exponential. So I'm just going to graph a regular exponential up here. Actually, let's take, here we go. So exponential functions have this type of this type of graph. So we'll just label what it is. This is just b to the x. Now, can you pick out some special features? Well, there's going to be two special features. One being that we now have a y-intercept here at 0, 1. Now, this is going to be true just for about all of your exponential functions. That is, if it does not have a shift up or down. We also have an asymptote. I'll draw that over here. So we also have an asymptote. This one is a horizontal asymptote. So now this again excludes when y is equal to 0. So you have these two features to be aware of. Now on this particular graph, right, this one is increasing. So when it increases, it's called a growth. So an exponential growth. This happens when your base b is greater than 1. So any number for your base is greater than 1 will have this graph that is increasing and growing up. Now, can you go ahead and pause video to find the domain and range? Your domain should be all real numbers, so you can go ahead and find all of your x values to plug in. Your range, though, starts from 0, non-inclusive, and goes to infinity. So let's try it again. If we have an increasing model, so an increasing or growing exponential, we could have a decreasing exponential. So again, we're going to take this format for your graph or for your function. I'll call this f of x is equal to b to the negative x. Now, what happens with that negative? Well, that negative is that flip over the y-axis. Or when you think about it, what do you do with negative exponents? Negative exponents allows us to then drop down into the denominator. Or it allows us to like flip your fraction. So write it like this. And again, this one has this particular graph. We're just going to go the other way. So that's this graph right here. Now, can you pick out your special features once more? And again, your domain and range. So we do have your y-intercept, and again, it's at 0, 1. We do have a horizontal asymptote here. At y is equal to 0. So our domain, once more, is all real numbers. And your range, again, is from 0 to infinity. Now, instead of increasing, we are going to be decreasing. So instead of calling this a growth, this is a decay, an exponential decay. This happens when your base is between 0 and 1. Again, you cannot be 0 and you also cannot be 1 for these restrictions. So if your base is a fraction between 0 and 1, we will have this decay. if the base is between 0 and 1, we have a decay. Whereas over here, if base is greater than 1, it is a growth. Okay, so that kind of concludes the shape of your exponentials, like just a rough sketch of them. And what we're going to do now is actually get a better understanding of what these graphs look like. So let's skip down to example 1, where it says sketch the graphs of the exponential and give the domain and range. So see if you can pause the video and attempt A and B, and all we're going to be doing is plugging in X values. And again, your X values, there are no restrictions on your X, but we can take a look at your base and determine, is it going to be increasing or decreasing? Well, because this 3 is a number that is greater than 1, we have an increasing graph. Base is more than 1, so we're going to increase. So we should have a graph that goes upwards. So now let's pick 3 to 4 values that we can plot and put on our graph. So let's just do -1, 0, and 1 to start. So you have f of x, or f of -1, is equal to 3 to the -1. Well, this is really just 1/3, right? If you have a negative exponent, it's now 1/3. So we have the coordinate -1 and 1/3. F of 0, 3 to the 0, is equal to 1, so 0, 1. And coincidentally, again, that is your y-intercept here. F of 1 is equal to 3 to the 1, which is 3, so 1, 3. And let's do one more. Let's put in a 2. F of 2 is equal to 3 squared, which is 9, so 2, 9. So again, if you don't know what these graphs look like, what we can start doing is just plugging in points that we're used to. And the more points that you want, usually 3 to 4 is a good start for your values to kind of just plug them in. And I'm just going to push these up here for a second. Here we go. So let's go ahead and plug in some of these points. You have your y-intercept. You have 1, 3. You have 2, 9. You have something like this. And then we can go ahead and connect your dots. And as best you can, try and connect them. And then we should not be crossing your x-axis because we do have that horizontal asymptote. So you can get as close as you can to it. We just cannot be equal to y is equal to 0. And try and get as close as you can. There you go. So let's have you pause the video and try it again once more for your other one. Again, if you can, try to pick out, try to tell me if it's a growth or a decay, and pick out about 4 points. All right, so now you see that this function here is 1/2 raised to the x. So this being a fraction that is between 0 and 1, we do have a decay. Base is between 0 and 1. And you could also similarly write this as 2 to the negative x power if we wanted to take the reciprocal of it. You should be familiar with both forms, but definitely if you see it in this latter form, that we want to put it into this first form. So let's go ahead and pick some values. 3 to 4 would be a good value. So we have f of x is equal to 1/2 to the x here. So let's try to pick just the first 3 again. So let's take a look at this -1. So f of -1 is equal to 1/2 to the negative first. We have a negative exponent, so we're going to flip upside down your fraction or just change position. So we're now at 2 or 2 over 1. So we have negative 1, 2. Let's do it again for 0 to the, oops, sorry, 1/2. It's 0 is equal to 1. So again, your y-intercept above 1 is equal to 1/2 to the first, which again is 1/2. And that just means if I wanted an additional point, maybe I wanted 4 points in total, or maybe on the test I want 5 points, I might want to choose a negative exponent because that'll allow us to flip your exponent or flip your fraction. So you now have 2 squared, which is 4. So you have negative 2, 4 here. So let's go ahead and plot these points. We have negative 2, 4. We have 1, 2, that one, and right here. So connect your dots. And going up. Again, drawing your horizontal asymptote. This is at y is equal to 0. On the test, I will have you draw or write your horizontal asymptote because your asymptotes, as we're going to be seeing pretty soon, they can change. They can shift up and down with your graph. Now, see if you can pause the video here and determine your domain and ranges. And then we're going to go on to example 2, where we talk about these transformations. So here we have your domain as being all real numbers, and your range is going from 0 to infinity. And on the other side, it is actually going to be the exact same for your domain and range. Let me throw that over here. Now, with your transformation, your domain and range will also change. Well, not so much for your domain, but your range will also change. Now, let's take a look at what those transformations might look like. So in example 2, all rules are still going to apply. Now, when it comes to your parent function, keep in mind what we've talked about before is that when you erase all of your transformations, whatever is left is your parent function. It's your original function. Now, think about all of the rules that applied from the last time, right? Things on the outside that shift your graph up and down, things right next to your variable will shift it left and right. Negatives unattached to your variable will reflect over the x, and then the negative that's directly attached to your x, that will allow us to, as we see, flip your fraction here. And it just reverses it on the other side. So see if you can pause and determine what your shifts are or what your transformations are. Well, here we have this +1, and keep in mind your exponent is all the way up here, and it looks like this is -3 to the x, and then down below, what we're going to do to this graph is then go ahead and add 1. So we are going to add 1, meaning that we're going to shift up by 1. Now let's try it again with, let's see what this negative does. This negative is not directly attached to your x value here, so we won't have a fractional base. But instead, if it's not attached to your x, this will reflect over the x-axis. So now let's take away all of your transformations, and whatever is left should be our parent function. So your parent function is g of x is equal to 3 to the x, which is coincidentally the exact one that we've graphed from before. So your parent graph is this one here. So if we want to put your parent graph, so parent, we'll say is f of x is equal to is equal to 3 to the x. Now let's go ahead and pause this video and quickly sketch a graph. So for me, quickly sketching a graph is pretty easy because I'll just take this graph right here. I'll put it right there. Now, before we said, okay, our graph should look something, should look something like this. Right here, we had -3 1/3. We had 1 2 3. So we rose up pretty high. This is our parent graph. Uh-oh. All right, so this is our parent graph. This is f of x is equal to 3 to the x. And we just said, okay, well, we're going to now reflect over the x and then shift your graph up 1. So keep in mind your reflection is right here. Let's see if I can decrease it a little bit. Your reflection is right here. So that just means all of these points are going to be reflected down. So these points here are now reflected. And now we're going to take these points and we're going to shift them up by 1. In doing so, right, shifting up by 1. So up here, and up. Oh, there, and there. There we go. So this is your new graph. Now, not everything here on my graph has been shown to shift up. Well, now we've shifted all of these points up by 1, but now we need to work on your horizontal asymptote. So your horizontal asymptote originally was at y is equal to 0, but when you shift your graph up by 1, notice where this graph is going to start flattening out. Well, that is where our horizontal asymptote is going to lie. Ooh. So your horizontal asymptote here is now at y is equal to 1 because we're going to add 1 to your transformation, to your end function. We said +1 here, and that is because we added 1 to transform up and down. Now, what is your new domain and range? Well, your domain here is all real numbers, and your range, we're going from -infinity all the way up to 1, and we are not including 1. So hopefully that makes a lot of sense. We're going to try it again with your next one. So you have h of x is equal to 1/2 x plus 3. So we're going to take a look at this transformation, which our transformation, you'll notice that we have a +3 here, and it's directly attached to your x value up in the exponent, rather than down here, it's saying +3. So when it's attached above with your x, it's going to allow us to shift left and right. Now, it being a +3 means that it's really negative. So we're going to be shifting left by 3. Now, when we take away that shift, we're left with the 1/2 raised to the x, and that would be your parent function. So we'll call this f of x is equal to 1/2 to the x, which is your parent function. Now, we've already graphed this parent function from before. Well, let me try to grab that one more time. We've already graphed this parent function from the above. So our graph should look like it is decreasing. So it is a decay. And I realize now I did not write decay over here. No, I did. So it is a decay. So let's go ahead and do your transformation. So you're going to take your graph here. Let's see, we had 2 to 4. So this was your parent graph. This was f of x is equal to 1/2 to the x. And now we said we are going to take this graph and its horizontal asymptote and shift everything to the left by 3. So that means each point gets to move 1, 2, 3 to the left. 1, 2, 3 to the left. 1, 2, 3. Ooh. So your graph should look something like this. So this is h of x is equal to 1 over 2 x plus 3. Now, do we need to now shift over your horizontal asymptote? No, because even if you were to shift some of these values over, right? Let's see, -8, we could shift over here, and -4, we could shift over here. Notice that it's not going to change, right? We're still at y is equal to 0. So that just means your horizontal asymptote will only be affected when you are shifting your graph up and down. Now let's take a look at your domain and range. Domain is all reals, and your range, again, hasn't changed. We're going from 0 to infinity. Now let's have you graph one more. Actually, let's have you graph C. I'm trying to think, do I like C? Let's change your base at the very least. We're going to do a base of 3. I'll just rewrite this. I want to graph 3 to the negative x using your transformations. Now, with your transformations, we said this negative that was on one of your outside ones, we had a negative on the outside, which reflects it over the x-axis. Now, this one being directly attached to your variable here is going to reflect it over the y-axis. So if we were to take this away, we're left with 3 to the x as your parent function, which we again have graphed before, which maybe I should have done a different one. But we're going to take that one. Say, let's see. 3 and 9. So we're going to take this parent function, which is, I think, we'll call it g of x. G of x is 3 to the x. Your parent is g of x is equal to 3 to the x. And we're going to take all of these values, and we are going to reflect it over the y-axis. Your y-axis being right here will start to then reflect each value over. So what was on that side will now come over. So we're now over here, and we're over here. That one stays put, and now we're over here. So when we connect your dots, and does our horizontal asymptote change? No, your horizontal asymptote does not change here. So we're just going to thicken that up just a little bit. Keep it here at y is equal to 0. And this is f of x is equal to 3 to the negative x. So if we started with a growth, right, we were growing up, and now we're left with a decay. The reason for that, and you may have spotted it before, is that we rewrote any sort of negative to then have a positive exponent. So we could have rewritten this to say, okay, we're going to flip it upside down and then make your exponent positive. So we can now just see that your base here is a fractional exponent or fractional base between 0 and 1. So it's a decay. Or you can take what you know about your reflections and your transformations and go ahead and give it a graph. Now, the other part of our video today is just going to be solving exponential equations, and this is called elementary cases. So when in this form, your bases, and we're talking about your bases here as a to the x is equal to a to the y. Now notice that your base here is the exact same. It's the exponents that are a little different. So if the bases are the exact same, what we can do is go ahead and ignore the base and solve. So step one, we want to isolate the exponential term. So get the exponential terms to one side. Now we have to rewrite them so that they have the same base on both sides. Lastly, we're going to set your exponents equal to equal to each other and solve. So for example, a. So thankfully, our exponential term, so 2 to the x, is already located on one side. Then it's set equal to 4. So we want to know, okay, well, this can be rewritten, thought of as 2 to the what exponent is equal to 4. Now, in some cases, it might be a little bit more challenging. So we need to start thinking as a way of changing this 4 to have a specific base. We want this 4 to match your exponential base. And sometimes it might require us to change both bases. So we're going to say 2 to the x. Now, how can we rewrite 4 to have a base of 2? Well, it just says 2 to the what power can be 4. Well, 2 to the second power, come on, 2 to the second power can be equal to 4. So now once we have your bases to match and they're the exact same, we're going to take a look at your exponents. We said we can now ignore your base and let your exponents be set equal to each other. So x is equal to 2. Now we can always check your answer. Let's say x is equal to 2 by plugging it back in. 2 squared is equal to 4. 4 is equal to 4. And that is a true case. Let's try it again on B. We have 25x minus 125. Now notice that your exponential term, this term, is not alone on one side. So we want to get it to one side. So let's go ahead and move 125 over. So we now have 25x is equal to 125. And now we need these bases to match. So what sort of number multiplied by itself a few times will get us to 25, and then again equal to 125? Well, that base would be 5. 5 to the what will get us to 25? Well, 5 squared will give us 25, and we still have your x as an exponent is equal to, and then again do the same. 5 to the what exponent is equal to 125. These are all just asking us 5 multiplied by itself 2 times, or 5 multiplied by itself 3 times gets us to 125. If we're not certain at all, if we know that 25 and 125 has a 5 in common, I can start multiplying. 5 to the first is equal to 5. 5 squared is equal to 25. 5 cubed is equal to 125. You're just multiplying 5 a certain number of times. 5 times 5, 5 times 5 times 5. And you can keep going until you get your number. Now that it's in this form where we have your bases the exact same, before we just go ahead and ignore them, let's clean up your exponents. Now we have an exponent being raised to another exponent. We learned back in chapter 1.2 what to do in this case. Well, if it's raised to another exponent, we will multiply your exponents. Multiply the exponents if raised to another exponent. So we now have 5 to the 2x is equal to 5 cubed. Now we can go ahead and ignore your bases. So you have 2x is equal to 3. And now let's go ahead and start to solve. So x is equal to 3 over 2. Now let's go ahead and check that real quick. So if we know that x is equal to 3 over 2, so let's say 25 to the 3 over 2 minus 125 is equal to 0. Well, again, back in chapter 1.2, we learned what this fractional exponent is. It's really saying that this is 25 underneath the square root cubed. Now, would we rather cube this 25, or would we rather square the 25 and then cube it? Well, perhaps we want to square the 25 first, so that'll give us 5 cubed minus 125. Well, that's 125 minus 125, which is equal to 0, which again is a true statement. Now, let's have you try C and D. So hopefully you pause the video and are attempting C and D. So 9 and 27, right? So what number times itself a few times can get you to 9 and 27? Well, 3 to the first, that's just 3. 3 squared, that's 3 times 3, that's 9. And 3 cubed, that's 3 times 3 times 3, which is 27. So we're going to be working with 3's. So this just says 3 squared to the x is equal to 3 cubed to the x plus 1. Now we have now a binomial above, so it's going to act together. So anytime you have a binomial, we want to put it in parentheses. So now let's clean up your exponents now that your bases match. We multiply your exponents. So we have 3 to the 2x is equal to 3 cubed, 3x plus 1. If we wanted to take it a step further, right, our next logical step, we could distribute 3x plus 3. So now let's go ahead and ignore your bases now that your exponents are nice and clean. 2x is equal to 3x plus 3. And now let's go ahead and start to solve. So solving, we might want to consider bringing 3x over. So we're left with negative x is equal to 3. Therefore, x is equal to negative 3. And again, let's check. When x is equal to negative 3, we have 9 to the negative 3 is equal to 27 to the negative 3 plus 1. So if we're looking at 9 to the negative 3, now, again, do we really want to do 9 to the negative cube, even if we dropped it into the denominator? Same thing with your 27. Do we really want to take the square of that? Perhaps not, but we can work towards, because we don't have a calculator, we can work towards putting this 9 back into a 3. Oops. So on this side, right, rewriting 9 to say 3 cubed to the negative third, we now have 3 to the negative 6. And on the other side, if we were to do the exact same thing, 27 is really just 3 cubed to the negative 2. Therefore, we have 3 to the negative 6, which again, as long as they are the same exact statement, these are going to come out true. Let's try it again with D. So we have 8 and 2 as your base. So 8 will be 2 cubed to the y minus 1. And again, there's a binomial, so let's go ahead and put parentheses to the 2 negative first. Now let's go ahead and clean up your exponent. We have 2, 3y minus 3. We can go ahead and distribute that in if we prefer. And now that your bases match and your exponents are nice and clean, we can come bring them down. Add 3 to the other side. Divide by 3. And again, check your solution. So now let's go ahead and check when we have 8 to the 2 over 3 minus 1 is equal to 2 to the negative first. So now we have 8, and that's really just 3 over 3. So now we're working with negative 1/3. Let's go ahead and drop these into the denominator. So we have 8 to the 1/3 is equal to 1 over 2. Now we have that fractional exponent of 1/3, which is just another way to say the cubed root of 8, which the cubed root of 8 is just kind of the reverse of cubing something. So it's just saying what number times itself 3 times is equal to 8. Well, we already established that that is 2, which again, a true statement. Now, what we've done here is called elementary cases. We can solve your exponentials without having to use a calculator, without having to use its inverse, in order to solve your for your variable. Again, this can be done by matching your exponents or matching your bases, getting your exponents to drop, and then we take a look at what the value is. So that is called an elementary case. Now, their last thing for chapter 6.1, which is actually 6.2 in our textbook, we are talking about E. Now, E is actually a number, and it has the equation 1 plus 1 over n raised to the n. Now, let's try to do some little discovery. So if you have a calculator, let's have you take that out. And what we're going to be doing is determining rounding to 3 decimal places. Well, what is E? So E is, as we established, a number, and we're going to discover what that is. So if we have n here, n being 1, we're going to plug in a 1 into these values. And then we're going to do a 5 and a 10 and a 100 and 1,000 and so forth. Now, you don't need to do all of them if you're working at it at home. I would just maybe do the first 2, maybe this middle one, and maybe this last 1 or 2. So let's take Desmos. That's my wrong one. Now we had the formula 1 plus 1 over n. N in our case is going to be 1 for now. Raised to, I do the raised to button, there we go. Raised to the n, so raised to the first. Now that'll spit out a 2. So right now, E we know to be 2. That is when n is 1. Now if we were to do a different number, let's say when n is 5, it's now 2.48832. Let's do it again. And I want to round to a lot of decimal places here today. Let's do 10. So it's now 2.5937. So we started out at 2, 2.49, 2.59. Let's tack on 100. 2.471 or 2. Let's do 1,000. Oops. That number was incorrect. 2.717. Let's add another 0. 2.7114. Okay, now we've seen this 2.71 or 2.72 a couple times. So now let's keep going. We now have 2.71826. One more. 2.71828. 828. I cannot say that number. So all in all, if I were to write some of these values down, we started out with 2, 2.48832, 2.593742, 2.704814, 2.716924, 2.718146, 2.718268, and 2.718280. So notice that it is a number of 2 and about it's estimated, right? Notice that this 2 so other than this 2, I should say, now that they all have a 2, they now are showing to all start with this 7. Then it goes from the 7 into the 1s. Then from the 1s into the 8s. And then you can see it with, again, the 2. So this is roughly, if we were to round it to 3 decimal places, E is roughly 2.72, or rounding to about 4 decimal places or 3 decimal places. Oh, I did say 3 and I rounded to 2. 2.718. And again, this is kind of going to be like pi, where pi is considered an irrational number, because this continues without bound and it's not repetitive in any sort of nature. Now, if we were going to use E on your calculator, we don't need to use this number. What it has done is it's programmed E into the calculator for us. Now, if on a graphing calculator, notice that there's 2 locations for it, which if you can pause video and try and figure that out, kind of like a little scavenger hunt. E is located in blue, so blue letters, meaning they're a little bit smaller. On the left-hand side of our calculator, it's located right above ln and right below log, which is kind of by the numbers 7 and 4 on the left-hand side. So to get it, we're going to hit this second blue button up at the top and then ln, and that'll allow us to raise it to any sort of number here. So if I just did it to the first power, we have 2.71828-ish. Now on the other end, your E is located again in blue, right on top of your division sign. So we can also hit this one. It's not that there's any sort of difference. It just means that this number, if you wanted to raise it up to, raise it to have if you wanted it to have an exponent, you now have to actually use the little exponent button to then calculate. So there's no difference in those programs. It's just whether or not you need an exponent in your E. Now, E has a specific name. This is called your natural exponential functions. Now, if we were to graph it, notice that 2.718 is roughly about 3. So we would notice if we were to graph 3 to the x, e to the x, and 2 to the x, that it's more closely related to this 3 to the x value because it's kind of bordering 3. Now let's take a look at some applications of E. E shows up in exponential functions as a continuous compound interest and half-life of some substances. So it has lots and lots of context and information to it that is very useful in the math and sciences and business. So if we were to take this equation and pick it apart, in finance, it's also looking at FV equals PV, e to the RT. In this case, sometimes it's referred to as PERT because it looks like it's spelling the word PERT. Now this A amount, or FV, is your future amount. Future amount, future value, your worth, your end amount, your end value. So anything that is something that we haven't achieved quite yet. Your PV, or your P, is called your present value, or your principal. Principal. Your present value, your principal, your initial amount, your original value, anything that just says that you have this amount right here, right now. Now, E is just E, it's itself. R is your rate, and T is your time. So that is kind of the context of what these values are. I use a lot of this in Math 105, and you guys will be seeing a little bit of it here and there when we talk about some of the more math and science related version of it. So half-life of a substance, radioactive decay, that sort of stuff. So let's talk about example 4. It says a radioactive substance decay in such a way that the amount of mass remaining after T days is given by the function. So right now we give you the function. In the future, we'll talk about how to build some of these equations if we have time. It does tell us though that M of T is measured in kilograms. So it says find the initial mass. So how would one find the initial mass, the beginning mass, the original mass? Well, we can do this in one of two ways. Now, keep in mind, right? If we're talking about the initial of something, that means when t is equal to 0, right? No time has passed. Whatever it is, the clock hasn't started. So we could, if we wanted to, substitute in a 0 into your equation. Anything multiplied to the 0 is 0. Anything to the 0 power is 1, meaning that your initial mass is 13 kilograms. Now this 13, have we seen it before? Well, that 13 is coming here. This is the present value, the initial, the principal. It's just your starting amount. Now this 13, if we were to restructure it so it was showing kind of like a linear from our very beginning of the video, we said f of x is equal to a times b to the x, right? Notice that 13 is acting as your a. This is called your multiplier. So it's just going to help our values grow or decay by a certain amount. Now let's try and see how much mass will remain after 45 days. Well, this just says t is equal to 45. So therefore, m of 45, we'll punch that into your equation. We'll get about 6.619 kilograms out. And yes, for your homework, please use a calculator because I think some of the problems, it will ask you for some approximated solutions. So this being your exact, this being an approximate amount, will need your calculators. On the test, I'm just going to be looking for the exact amount. So something that you would have plugged into the calculator. So that concludes our video for chapter 6. Again, this is covering chapter 6.1 and 6.2. For us, you don't have 6.2 homework. We've kind of just put those two sections together because they flow pretty nicely.